Good morning, good afternoon, good evening. Even though we originally started this webinar for just US, we have participants from across the globe. So thank you for taking the time in the late hours in those eastern part of the country, of the world. Welcome everybody. This is a webinar from IPCOS on optimal steam to carbon. This is mainly focused on reformers that are in various fertilizer plants, hydrogen plants, methanol plants, or even to some extent in refineries. Just before we go through the webinar, just a quick reminder, it's everybody will be muted. If you have any questions, please ask them through the Q&A and we will answer them at the end of the call. So this, before we jump into the topic, I would like to very briefly introduce about IPCOS. IPCOS is a 25-year-old company that has been doing business across the globe, and mainly this that is relevant to this group is related to how to improve plant operations. The topics that we usually help the operators are related to advanced controls, any help in the base layer, improvements in the base layer controls, do some studies to help these and attain business value cases and things like that, provide you training to do any of these items, and also alarm management to help you in your making sure your operator can breathe life when you have less alarms to come across. Which industries we do? As you can see, we do most of the oil and gas related, which is petrochemicals, gas processing, refining, chemicals, power, waste, utilities, and obviously fertilizers. If you look in across all of these, we have conversant with all major APC technologies, and the way we work is establish trust based on our track record, and based on that we get more and more projects from the same customers. And primary reason is because we have very good industry specific domain knowledge, and that helps us in delivering good value product applications for APC. We have done over 500 projects, over 40 countries across the globe. We have 7 offices, as you can see here, couple in Europe, couple in India, one in Middle East, and one in US. So this is our office base. With this, I would like to introduce you to our speaker for the day. Juan Carlos has a MSc in chemical engineering. He has over 12 years of experience in process control and optimization. He has done projects across the various industries I've mentioned before, which is oil refining, gas processing, petrochemicals, fertilizers, and utilities. Obviously, today's focus will be on ammonia, methanol, and hydrogen, and he is our best expert in this area. So without any more delay, I will pass it on to Juan Carlos, and Juan, take it away.
Thank you very much, Ravi. Yes, so well, the purpose of today for us to talk about the optimal steam to carbon ratio. Oftentimes, I wouldn't say it's forgotten, but plants operate at a constant steam to carbon ratio, and there are some gains there. You can try and optimize it, but the optimization of such an important variable in a plant is usually not a straightforward one, because many things need to be considered before you can decide how to optimize this parameter. So To give some type of flow to the presentation, we are going to focus mainly on steam reforming for ammonia plants, because that's where we can see with more clarity how can we optimize the steam to carbon ratio. It doesn't mean that it cannot be done for other type of plants that also use steam reforming. But since steam reforming for ammonia plants is, let's say, at a bit of a higher level of complexity, then we decided to go for this particular industry to focus our presentation on. So first of all, just a little reminder on what is steam reforming and how is it used for ammonia plants. Common control configurations for steam reformers. So then we're all on the same page on how are typically reformers controlled. And then we'll go and check the effect of the steam to carbon in the ammonia process in particular. So we will see how that single variable has an impact in many other parameters in the plant. And then we will give a couple of examples where, after studying in detail the layout of the plant and all the process conditions, we have actually come up with different solutions, because every plant will most likely require a different way of doing this. So steam reforming, I think most of us should know what steam reforming is about. The particular case we're studying here is steam reforming for ammonia plants. So the steam reforming is typically done with natural gas. Natural gas and steam get in contact over a catalyst to become syngas, which is basically hydrogen and carbon monoxide. There are some side reactions, as you know. And in the particular case of ammonia plants, you have a secondary reformer where air is, let's say, infused. It goes over a catalyst as well, and then further reforming happens, more hydrogen is produced. We can see here in the reactions, more hydrogen is produced, and then finally, to be able to get rid of all the carbon monoxide that has been produced in the previous two stages, then we have the HTS, LTS, or basically the water gas shift reactors. So in the water gas shift reactors, we have the water gas shift reaction happening, in which carbon monoxide reacts with steam again to produce CO2 and hydrogen. So the objective here is for this carbon monoxide to be minimized, and then we are left basically just with hydrogen and nitrogen. This is again the case for ammonia plants. We know that if we're talking about methanol, you don't have such a thing, because you are in fact interested in having carbon monoxide. You are interested in having syngas because your synthesis requires the syngas. But for ammonia, that's not the case. Okay. So talking about this, the common control configurations that you see in we call it primary reformer, because that's how it's called in ammonia plants, but this your typical steam reformer. So what are the typical control configurations you have? So basically the whole discussion we're going to have here is based on the fact that these controls are already in place in the DCS. If they're not, then of course, most of them will need to be implemented before you can try and do some kind of optimization, because they bring a lot of stability and control to the reformer. So to mention the most important ones, we typically have a reformer outlet temperature control. That's very important because the reformer outlet temperature usually gives you a very good indication of the level of conversion happening in the reformer. The reformer outlet temperature is usually strictly correlated to the methane slip, to the amount of methane that has not reacted inside the reformer. So having a control of this temperature already gives you some stability, because your methane coming out of the reformer will be more stable. Therefore, the conversion tends to be more stable. Attached to this reformer outlet temperature control, usually you find what is here described just as firing controls. You typically have something called a duty control. In the particular case of ammonia plants, your fuel is not just some more natural gas that you're burning to provide the heat of reaction to the reformer, but also there is the purge gas. So there's some hydrogen that has typically been recycled from the synthesis section of the ammonia plant that is then returned or recycled back to the reformer and then used as fuel. So this duty control is typically very, very important to have, because if you have changes in the amount of hydrogen that come to the reformer, then the amount of duty you're providing the reformer with changes. If you have a duty control, then you will change in a more in a better way. You will be changing the fuel gas that you're burning to keep your reformer at the desired conditions. Then as well, depending on how old the reformer is or how the configuration is done, you may have an induced draft fan and also a forced draft fan that basically puts and pulls the air from the reformer. And when using those machines, you can typically easily configure a draft control, draft pressure control, that's usually attached to the induced draft fan. And you can also, if you have the analyzer, which is often the case, create some excess oxygen control. This is very desirable to do. Obviously, if we're talking about very old reformers that have not been provided with such machines like the induced draft fan and the forced draft fan, then most likely you will have like a natural draft machine, reformer, and then your control will be based typically only on some damper on your stack to control the both excess oxygen and draft pressure. But this is naturally not a desired situation, but in any case, it happens. So it's worth mentioning that it's also the case. And then finally, what brings us here is the steam to carbon ratio control. So as for the steam to carbon ratio, we can see that in some places, there is an analyzer that is put in the stream, in the natural gas stream. So it gives you an analysis, continuous analysis of your natural gas. So if you have an analysis of the natural gas, you can calculate the carbon number. And if you can calculate the carbon number, then you can easily configure in the DCS a steam to carbon ratio control. That's typically the best way of controlling your steam to carbon. In other cases, because of the reliability or just because there's just not an analyzer available, then what we have seen is that a steam to gas control is configured. Either way, both structures will yield the result of keeping your steam to carbon in control. Steam to gas in an indirect way, of course, steam to carbon in a very direct way. And talking about these controls, we have also seen that there are typically two configurations about them. One, which is the one described here in the picture. You see how in this case, the The natural gas is the master controller for the ratio. So basically, the ratio between steam and gas is kept with the flow of gas as master. This is one option, but usually then it requires that your steam network is able to cope with constant changes in the steam supply. But there's also the option, which is described here, where in fact it is the steam that acts as a master. So the steam flow is the one that at the end determines the amount of natural gas that is introduced into the reformer. You have those two options, and depending on which one you have, then the way the steam to carbon has an effect on the process is different. It needs to be said because probably the optimization you do could also be related to that. I think it's clear that in the case of this second case, when the steam is the master, if you're changing the steam to carbon, which will affect definitely most likely the gas flow, right? Because you have your ratio controller as being the master of the gas flow. If you change the steam to carbon ratio, it will not be the steam who changes because that will be kept constant since the master. It actually will be your gas that will change. So it means that when you change the steam to carbon in this configuration, your throughput to the plant will change. And that has a major impact, of course, in the rest of the process, because the throughput is changing, so a lot of other parameters will be changing. It's not just the ratio, it's also the amount of production that will change. So in that sense, that also needs to be considered when trying to optimize the steam to carbon. So as I mentioned before, let's quickly take a look at what the impact of the steam to carbon ratio has on an ammonia plant. So when you change the steam to carbon, well, first of all, as I mentioned, the steam network itself is affected because the steam comes typically from a medium pressure steam network. And that network will most likely have other consumers. No, it doesn't necessarily need to be that the steam network only supplies the reformer with medium pressure steam. So there will be other suppliers and other consumers to the network. And changing the steam to carbon can definitely alter the balance of the steam network. So that's an initial impact that you can have. And as we will see, sorry, as we will see in further slides, that can become a deciding point when knowing what to do, when trying to know what to do with the steam to carbon. If the steam to carbon ratio changes, then based on the fact that we have a reformer outlet temperature control, then your fuel consumption will also change. This is clear. If your fuel consumption changes, then this should be your first clue that perhaps you need to find an optimum value for the steam to carbon where your fuel consumption is minimized, if that's what you intend to do. If you intend to optimize your plant towards energy savings, then your fuel consumption changes associated to a different steam to carbon ratio needs to be considered. There's the typical things we all know about steam to carbon. If you change the steam to carbon, especially if you reduce the steam to carbon, you start running into a region of operation where the catalyst inside the primary reformer can start to coke. Some coke deposition can happen on the catalyst. We'll talk about this a bit more in the future, but this is, at least for the case of an ammonia process, usually never the real constraint, because experience has shown that the steam to carbon ratio at which you can really start seeing some coke deposition is usually below 2.5, 2.4. And way before you reach such a value, you will find some other limitation in the case of an ammonia process. Then, even with a temperature controller in the outlet of the reformer, as we described before, if you change your steam to carbon, you will also have a change in the conversion. This is due to many things, partly because the partial pressure of the natural gas or of the methane in the primary reformer changes, the residence time changes, so many things change inside the reactor, and also thermodynamically, when you put more steam, since this is an equilibrium reaction, thermodynamically, you will also favor one of the sides of your chemical reaction equation. The change in your steam to carbon ratio, even with a temperature control, will change your methane slip from the primary reformer. And supposing that the air that is introduced into the secondary reformer is kept constant, the effect of this, the change in the methane slip will not only be seen in the primary reformer, but you will also see the effect of the steam to carbon ratio at the exit of your secondary reformer. So this needs to be considered. Usually the methane slip outside your secondary reformer is a value that you need to keep within some range. So if you're optimizing the steam to carbon ratio, you need to make sure that you're able to still keep your methane slip at whichever value that you are that you're supposed to reach here. Continuing on, if you change the steam to carbon ratio as we described earlier, we have the water gas shift reaction happening in both the HTS and LTS reactors. That reaction, as the name indicates, uses steam to convert carbon monoxide into CO2 and hydrogen. So if I, for example, reduce my steam to carbon, then I will start seeing effects on these reactors. In fact, often the case, that is the real limitation for your steam to carbon ratio if you find that minimizing it is what will bring you some benefit. It's not the coke deposition, most likely. It probably is not the methane slip, because chances are you will be able to fire up your reformer and still keep your methane slip constant. But then the carbon monoxide slip outside your HTS and LTS reactor, that one will change for sure once you change the steam to carbon ratio, because it will be just less water available to react with the carbon monoxide, so then the conversion will be reduced. And this we have found to be also one of the impacts of the steam to carbon ratio that impacts the way you optimize it. And then last but not least, if you're operating a maximum throughput, or I don't know, for any condition, summer conditions, you're reaching a lot of limits in your equipment, it could well be that the process water treatment system, because once the gas mixture comes out of the HTS and LTS reactors, it gets cooled, and then most of the water that still remains in the system is eliminated from the process. Well, that water needs to be treated, obviously, and we have found as well that that process water treatment system sometimes is the constraint. So if, for example, you see that you need to increase your steam to carbon ratio for whichever the reason is, well, we have found that sometimes your process water treatment can actually be your limitation when doing it. Because you can keep the same level of production at different steam to carbon ratios, but then changing the steam to carbon ratio changes the amount of water that needs to be treated. And if you're already struggling with your process water treatment, then that probably can also indicate to you what is it that you need to do to optimize the ratio. Okay, so a couple of examples. The first example is the optimization of the steam to carbon that we have done for a standalone ammonia plant. when we say standalone is that it's just an ammonia plant. It doesn't belong to any industrial site with other plants that share utilities. That's why we call it standalone, because no utilities are shared with other plants. So I think we all have heard the phrase that an ammonia plant is actually a boiler with a byproduct, which is ammonia. So it means that often a standalone ammonia plant has a surplus of steam. So there's no need for an auxiliary boiler to provide extra HP steam for the plant. And that was the case in this example. So there was a surplus of steam. So if, for example, you were thinking, oh, it's easy if I want to optimize my steam to carbon, I just reduce the steam to carbon because it's less steam, and then I'll be saving some energy by not having to generate that steam. But not the case here, because the steam is generated anyway, and if you don't use it, you need to vent it. So here we found that case. We also found a case in which the ammonia price was high, so there was a conversion to have a high. There was an incentive to have high conversion. The gas supply was limited. It was a purifier plant, so because it was a purifier plant, the methane slip coming out of both the primary and secondary reformers is a lot higher than what you typically find in a non-purifier plant. So whereas in a non-purifier plant, your methane slip at the exit of your primary reformer should be something between 10 and 12%, and at the exit of your secondary reformer is usually below 0.5%. In a purifier plant, those numbers are completely different. The methane slip at the outlet of your primary reformer is in the order of 28 to 30%. I mean, it changes. And then outside your secondary reformer is usually between 2 to 3%. So what this does is that the effect of the steam to carbon conversion is actually a lot higher, because you're not so close to the equilibrium of the reaction in the reformer. So based on that, we did all the calculation. We measured the effect the steam to carbon had in all of the parameters. We measured the effect of the steam to carbon in the methane slip, in the fuel gas consumption. We measured the effect the steam to carbon would have on production itself. And then what we found out was that because here the incentive was in fact to have high conversion but reduce the energy consumption, then maximizing the steam to carbon ratio up to close to, reduce completely the venting was the solution. Because in this particular scenario, increasing the steam to carbon ratio was actually, as is the case typically, reducing your methane slip. And if your steam to carbon ratio increases and reduces your methane slip, then you need to fire your reformer less to keep the same level of conversion. So just to keep the same level of conversion, you already need to fire less, just because of the steam to carbon is increased. You have more conversion basically. So at the end, after doing all the calculation and using all the costs, what we found out was that, maximizing it was the way to go, because it in fact reduced the fuel gas consumption, as you see here, by about 5%. So it was an important finding. And then we were at the same time utilizing the steam as much as we could, which was good, because then no venting was needed, or little venting was needed, to keep the same level of production. So as you can see, the answer is not just a single one. In this case, it was maximized. And then next example, this is just an ammonia plant that is part of a fertilizers complex. So it's not just an ammonia plant, it's an ammonia plant there. There's also an urea plant there. There's a nitric acid plant. There's many other plants in the same granulation plant in the same complex. So chances are we have a complex, then utilities will be shared. And since utilities will be shared, a lot of the steam that is generated by the ammonia plant is used not only by the ammonia plant itself, but also by other plants. Let's say your urea plant, so the high pressure steam that you're using, that you're generating in your ammonia plant is used not only to give energy to your syngas compressor, but it will also be the steam that you use to give energy to your CO2 compressor in your urea plant. So because of that, what we found here is that the HP steam balance is only met if an auxiliary boiler is used. So if you have an auxiliary boiler in operation, that auxiliary boiler is burning fuel to generate the additional steam. So that changes the picture completely from the previous picture where steam was, I wouldn't say for free, but let's call it for free, to steam that actually costs you money. So when you're doing your optimization, you're doing your calculation, you need to consider the cost of generating the steam here. And that changes the picture completely. On top of that, in this particular case, the ammonia price was low. So basically, the whole optimization had to be driven towards energy savings. There was limited process water treatment capacity. As I said, I call it old plant, but I mean it's a non-purifier plant, so it's a low methane slip coming out of the primary reformer. So basically, the effect of the steam to carbon ratio on the methane slip is smaller. All that plays a part, and then you have also ship reactors that were slightly undersized. So after computing all these factors, what we concluded was that actually, in this case, minimizing the steam to carbon ratio was the way to go for energy savings. And the most important constraint that we found for this optimization was the carbon monoxide slip coming out of the ship reactors, which you think, okay, is way downstream the reformer itself. That's why we call this presentation Look Beyond the Reformer. There, the effect was all the way at the exit of your HTS, LTS reactors. But that's what we found, that is what we needed to use to know how much we could really minimize this steam to carbon ratio. It was not because of coking problems, not even close. It was because of the carbon monoxide slip from the ship reactor that we really had to limit. And on top of that, the process water treatment capacity was limited. So reducing the steam to carbon meant less steam coming into the plant, which meant less water going to the process water treatment system. So it all played a part in concluding that minimizing was the way to go. And then by doing that, we also managed to reduce the energy consumption, or better said, to improve the energy efficiency of the overall plant, because that's what we do. It's the overall plant that we look at, and that's how we decide where to go. So in total, the results were 1.2% reduction in specific energy, measured as gigajoules per ton of ammonia produced. So yeah, it was a nice project to do. So how was this optimization realized? Well, in both cases, we used our technology. It doesn't mean that we're stuck to our technology, of course. It's a multivariable predictive control technology, of which there are plenty. It's just that ours is really good. So using this tool, we were able to, first of all, measure and identify process responses. So we could quantify things like what's the exact effect of the steam to carbon ratio on the methane slip. So because we could quantify it very precisely by using the data, then that allowed us to make a very accurate calculation. And then once we had that, we were able to configure the objective function that our multivariable predictive control uses to optimize in the direction that we found that was the best. As well as is typically the advantage of using multivariable predictive control, complex control problems can be addressed. So we have multivariable interactions. That's typical when you're doing an multivariable predictive control implementation. Low and higher order dynamics. So just to give an example, with this solution, we were not only looking at the reformer, we were also looking at the synthesis section of the ammonia plant. So a very important parameter in an ammonia plant is the hydrogen to nitrogen ratio, which you can only change when you change the air that goes into the secondary reformer. But the thing is, because it's a huge synthesis loop, if you make a change in the air that goes into the secondary reformer, it typically takes 6 to 10 hours for you to see the final effect in your hydrogen to nitrogen ratio. And that's something that is very hard to do with normal and typical PID controls, and is much better addressed with a multivariable predictive control. And then the fact that because this is working online 24/7, then the benefits could be sustained continuously. All right, so yeah, it was short and simple. I hope you enjoyed the presentation. Questions?
Thank you.
Thank you,
JC.
Chat boxes, yes.
Thank you, JC. That was a really good presentation. We have a couple of questions, and I think we have addressed it, but I think it's good to recap them anyway. So I'll read the question for you. What limitations that we can measure that you will see when we try to minimize steam to carbon ratio from 3 to 2.5?
Yeah, as I mentioned before, if you are working with an ammonia plant, way before you reach that value of 2.5, you will see the limitation of your carbon monoxide slip from the shift reactors. That's most likely the case. I don't think you are able to go lower than 2.9, maybe 2.85. Depends on your shift reactors, obviously, because but even theoretically, if you make the calculation, there's a minimum that is hardly below 2.85. So yeah, that's usually one of the limitations you will find if you're trying to reduce all the way to 2.5.
Thank you again. We have one more question. In reformers, minimum steam to carbon ratio is given by the licensor based on the plant load, and the ratio increases and decreases in the plant load. How can we challenge this if we can control the CO slip?
So thing is, of course, licensors give you a steam to carbon ratio or steam to carbon ratio table, like for the case of hydrogen plants. In hydrogen plants, usually you have like a steam to carbon curve that is based on the throughput, basically on the load to the reformer. At high loads, you can typically operate at lower steam to carbon, and the other, and of course the contrary is true. So in those cases, the licensors, they work out some numbers that they can guarantee are always safe to use. So there's this gap that you can still take advantage of. So even though the licensor is telling you to keep it at a specific value, you need to realize that that value that the licensor is giving you is just to be absolutely safe. At the end, that's their job, right? To commission a plant and leave it running and not hear from the client again, because that's what their fame comes from, right? If the good name of a licensor is based on how good are the plants, how reliable are they. So that's why they give you those numbers, but those numbers are typically very conservative. So you can challenge them, as I said before. You can just start using all the measurements you have around, and then make a study and see if you can actually challenge those values.
Then maybe a follow-up question would be, you touched upon it earlier. Is there a chance of coking?
Oh, chance of definitely. I mean, if you go too low, yes, for an ammonia plant, if you identify your constraints, your chances of coking are zero basically. So no, I don't think there are chances of cooking if you really know the process.
Okay, thank you. Let's talk about other challenges that typically are faced by the operations. In the primary reformer, we have the oxygen control and the pressure control in there. Typically, it's very difficult to control that. So how do IPCOS address these challenges?
Oh yes, yeah, exactly. So as described initially, you have your induced draft fan and your forced draft fan that is controlling the amount of air that goes inside the reformer chamber. In those two controls, the draft control and the excess oxygen control will tend to interact with each other. Naturally, if you change the amount of air that goes into the reformer, then the draft pressure will change. And conversely, if you change the amount of air that you're pulling from the reformer, then the amount of the flow of air that goes into the reformer can also change. So that interaction is, in fact, a challenge that you need to deal with. That is not a multivariable control problem per se, but we as IPCOS, we have specific software that allows us to do the PID tuning for loops that have interactions between them. So it's not your typical PID tuning software that just helps you tune one by one your PID loops. In fact, here you can put any amount of PID loops that you want in as a single problem, and then the software will find the best tuning that makes both controllers work properly. So basically, those interactions are taken into account when the software calculates the PID parameters, and that's how we can address that issue.
All right, thanks, JC. Here's another question from one of the participants. A low steam to carbon can cause carbon formation on the reformer catalyst, but this is a slow process, as you just mentioned. How do you constrain the steam to carbon appropriately in an MPC to account for the long-term impact? Are you going to just rely on the licensor guidelines for this minimum steam to carbon, or is there a different approach?
I mean, as I said, yeah, it is a slow process. That is true, but it's a slow process if you really are operating at very low values. So with the MPC, for sure, there will be some guidance that we will follow to establish as limit for the inputs, for the manipulated variables, as they're called in the MPC. So we can make sure that our manipulated variable, in this case, the steam to carbon, does not go below a certain value that you can establish. Let's say it's 2.8. So we know that below 2.8, you can start having some carbon deposition. Chances are, I don't know, basically, we know it's more towards 2.5, but anyway. But we can make sure that with APC, once you put the limit there, so that's why it's so important. I think the question also, sorry, leads me to something else. That's why it's so important to have a steam to carbon ratio control in the DCS, because that way we can use it in the MPC as a manipulated variable. And when you put limits to the manipulated variables in the MPC, those limits are hard limits. They're always respected, always respected. You will never go below or above the limits that you have established. So based on the fact that you have some automatic control of your steam to carbon and you use that as manipulated variable for the MPC, you can put those hard limits on your manipulated variable, and that way make sure that you don't run into the conditions where the coke deposition can happen. But again, as I said before, chances are you will not even reach those values. You will most likely find your limitation somewhere else way before you reach those values.
Hey, thanks, JC. Maybe a leading question to that one would be, different licensor, process licensor, gives you different limits, different approaches. So how does our approach change based on the process licensor?
Yeah, I mean, it depends. It is true. Well, our approach is always the same, and it's a very systematic approach. The first thing we always do, we just don't come to a plan and say, oh, you need to do this, you need to do that. No, way before we give any recommendation, what we do is we study the process. We study the process in as much detail as possible. We get as familiar with the process as we can, and only then we give some recommendation. So the different configurations that you see from different licensors, well, we have process knowledge. That's our know-how. So we know what impact can have in the rest of the process, and based on that, based on each licensor design, we assess how feasible is it to do certain type of optimization.
All right, thanks again. With this, we have come to a conclusion. Oh, there's one more question that popped up. Okay, let's see. In general, do you maintain the DCS level cascades as is or just manipulate the set point of the master controller? For example, reformer outlet temperature to duty, cascades, and excess oxygen to dampener. How do we take care of those?
Yes. Yeah, we typically try to first optimize and do as much control as possible in the DCS itself before going to the MPC solution. So yeah, as you're mentioning here, the reformer outlet temperature control, we keep that cascade with the heat duty. Yes, with the duty control, we keep it because it makes no sense for us to break that cascade, since that cascade is already rejecting a lot of the disturbances that can come in the process. And as I mentioned before, you can have hydrogen purge flow that is changing, or you can have just a change in the composition of your natural gas that you're burning. So any of those changes, if you can reject those disturbances in the DCS is faster than the MPC, so it's much better if we reject those disturbances in the DCS and then you use the MPC for what is really made for, which is more the optimization part of it. And then, yeah, you mentioned that the heat cascade is cascaded to the excess oxygen. Is that the case?
Yeah.
I'm not so sure because I mean, at least I haven't seen that. But if it's working, there's no point in us removing it. I can imagine that this is related to the duty control being somehow a measure of the load to the reformer, and based on that load, then you can try and control the excess oxygen. But an excess oxygen control is, in fact, most of the time based on the airflow a lot more than on the fuel flow. Although both of them have effect on it, obviously, it is usually the airflow that has the effect on the excess oxygen. So there will most likely be some type of control that changes the amount of air that goes into the reformer to control the excess oxygen.
Yeah, I think we typically see oxygen to dampener cascade.
Exactly, yeah.
Not usually to duty control. Okay.
To duty control, yes. No, yeah. I don't think that's very common.
Yeah.
I'm not saying it's not possible, but yeah, I mean.
That's not a common way. Okay.
Yeah.
All right. Well, one more follow-up question that came up. What's the difference between various APC softwares, and what is the main criteria that that impacts for a good implementation?
Yes. Most of the multivariable prediction control softwares are based on very similar algorithms. So we have worked with many. Let me turn around the question. We have done this using many different technologies, and we have always managed to achieve good benefits. So basically, regardless of the MPC technology that you use, I mean, provided that is one of the common ones, let's call it DMC, or I don't know, RMPCT or PACE or Inca. As long as it's one of the typical ones, I think we should always be able to address the issues and do the optimization. So I wouldn't say there's that much difference in that sense.
Yeah, so basically it's not the software that is, it's the people who are doing that is important.
Yes.
Is what you're
yes,
getting.
yes, exactly. As I said before, what we do first is really go and understand the process and find out how to optimize the plant.
Yeah.
And then the technology is just a tool. I mean, of course, as any tool, if it's good, it really helps. But we managed to do it regardless of the technology because of our knowledge.
Yeah. The next question looks like a little more detail for here, but I'll ask it anyway. You can summarize it. Did you typically perform a benefit assessment before APC? Answer is yes. If so, can you share how you typically perform the assessment study? Maybe a short one. Yeah.
Yes. We can also take this separately, of course, and give you more detail. But just as a very quick answer, we do, yes, perform these benefit assessments before, always do, measure the benefits. Obviously, we can report those benefits in terms of engineering units, or if there's some non-disclosure agreement that is signed and you are happy to provide us with also economic figures of prices of utilities and products, we can also, of course, report the same benefit assessment in monetary values. But either way, a monetary value or engineering units, we can do that. And the approach is the same. We go and get to know the process. So typically we ask for some documentation about the process that you have. If you can share some PFDs or PNIDs and some process descriptions. And then we make some interviews with operations and process engineering. You get to know details of the process. I mean, in any case, we're familiar with the type of process. So our questions will be very focused on what we're dealing with. And then once we have an idea of how the optimization can be done, then of course we formulate some, let's call them theories of how the optimization can be done. And then to quantify if those chances for optimizations are true, we perform a very small step testing, a little testing in the plant. So we ask you to make some changes in the plant. So maybe change the reformer outlet temperature up and down a couple of times. And why do we do that? Because every plant is different. So then that way we can measure the actual and accurate effect of the different variables, of the different handles in the plant on the variables that we're interested in. And then using those results that basically are results that come from the data that we have obtained from your plant and your plant only, not from other plants, then we use those results to calculate the possible benefits. So that's usually how we do.
Yeah. Thank you, JC. There is a separate webinar available on our YouTube channel regarding how we do performance studies and things like that. So if you are interested more, please go there and get that webinar. If you can't find it, please send me a request and I can send you the link to that. All right. Thank you very much for your participation today. Yeah, there are some wonderful questions here, and if some questions are not answered, we will be sending them as a reply to you outside of this webinar. Thank you again. The recording of this webinar will be posted on our YouTube channel, and a link will be sent to you. And if you need any specific questions, please feel to reach out to us. Thank you once again. Bye-bye.
Thank you all.